The figure shows a cantilever thin-walled section subjected to forces as shown in figure in both x directions and y directions. And you can see here the cross-sectional dimensions of this thin wall having uniform thickness. Again, in the problem it is stated that we have to neglect the squares and higher powers of thickness while computing the sectional properties. So the problem statement is, it is required to calculate the directions due to bending at halfway of the beam and also at the built-in end of the beam. Okay, we have to find out the directions due to bending due to these loads. What would be the directions due to bending at halfway along the beam and also at the fixed end or built-in end of the beam. So this is the figure. Okay, so I have marked some 3 corner points, 1, 2, 3. So these are the cross-sectional dimensions given. All the dimensions are millimeter here, and I have taken 2 sections, 1 and 2. This is section 1, section 2 for computing x bar and y bar. So where I have to find out x bar and y bar, I have to locate the center of the x axis, y axis in order to calculate ixx, iyy, ixy. Okay, so now what is the formula for x bar? X bar is equal to a1 x1 plus a2 x2 divided by a1 plus a2, right? And y bar is equal to a1 y1 plus a2 y2 divided by a1 plus a2. Now I have taken 2 sections. Let me treat or consider this point 2 as my reference point to calculate x1, x2, y1, y2. Okay, so this is my reference point. So x1 is equal to section 1. So treat this as a line. So x1 is nothing but 36 divided by 2, 18 millimeter. And x2, this is section 2. Treat this as a line. So x2 would be 0. And what is y1? y1 for section 1. Treat this as a line. So y1 is 0. And y2 is equal to 24 divided by 2, 12 millimeter. What is A1 area? Area of section 1. 36 into 1.5. 36 into 1.25. What is the area A2? Area 24 into 1.25. So we have to find the area A1 and A2, so that when you substitute A1 and A2 in this formula, you will get, for example, A1 is 45 mm square and A2 is 24 into 1.25, which is nothing but 30, right? 30 mm square. 30 mm square. Sorry, A2 is 24 into 1.25. A1 is 36 into 1.25. So A1, A2 we have got, x1, x2, y1, y2. If you substitute here, you will get x bar is equal to 10.8 millimeter and y bar is equal to 4.8 millimeter. So now we have obtained the x bar value and y bar value. Now we can locate the centroidal x-x axis and y axis. So x bar is 10.8. To the right of the reference point, you can locate the y axis. That is 10.8. So this is my y axis, x bar. So 10.8 millimeter. Then y bar is above the reference point to 4.8 millimeter. So this is my x-x axis, location of x-x axis. So which is nothing but 4.8 millimeter above the reference point 2. So now we have located the centroid. Now it is required to find the ixx, iyy and ixy. Now let us find Ixx, the centroidal moment of inertia about x-axis. So I have written all the values x1, x2, y1, y2, a1, a2, x bar, y bar, so that it will be easy for us to calculate Ixx. Ixx is equal to BD cube by 12 plus area into vertical distance square. So Ixx is equal to, for the section 1, 36b into 1.25 BD cube by 12 plus area of the section 1 is 45 into vertical square, that is section 1. So y1 minus y bar the whole square, y1 minus y bar the whole square. This is for the section 1. Then for section 2 BD cube by 12, 1.25, okay, b, d is 24 cube by 12 plus area a2 is 30 into y2 minus y bar, the whole square. So if you just calculate, so Ixx is nothing but 4032 mm power 4. 4032 mm power 4. This is the Ixx value. Now let us calculate Iyy. Okay, so Iyy is equal to dB cube by 12 plus area into distance square. So distance is nothing but x minus x bar the whole square. So for the section 1, dB cube by 12, 1.25 d, b is 36 cube by 12 plus area of the section 1 is 45, x1 minus x bar, x1 18 minus x bar is 10.8 square. So this is for the section 1 plus section 2 dB cube by 12, d is 24, b is 1.25 cube divided by 12 plus area of the section 2 is 30, x2 minus x bar the whole square, x2 is 0 minus x bar is 10.8 square. So remember always, I told you in the beginning itself, while computing the sectional properties, higher powers of t can be neglected. Okay, so here this is the higher power. The previous power, while calculating this Ixx also, I have neglected the first term for the first section. Okay, so 24 into 1.25 cube divided by 12 t cube higher power. I am just neglecting it. So when you just calculate, so I get the term to be 10692 mm power 4. So this is the value, that is the moment of inertia value about y axis. Okay, about y axis. Now Ixy, the product moment of inertia, how to find Ixy? So the product moment of inertia Ixy is nothing but area into x minus x bar into y minus y bar. So area A1 for the section 1 is 45, x1 minus x bar 18 minus 10.8. All the values are available here. We just take it. y1 minus y bar, y1 minus y bar, y1 is 0 minus y bar is 4.8 plus A2, section 2, A2 is 30 into x2 minus x bar, x2 is how much? 0 minus x bar is 10.8, then y2 minus y bar, y2 is 12 minus y bar is 4.8. So when you just calculate, so I am getting minus 3888 mm power 4. So this is the product moment of inertial value. So now we have calculated Ixx, Iyy, Ixy. Ixx, Iyy, Ixy. Just plug in these values here in this bending stress expression. Now we need to calculate mx and my. So in the problem statement it is given, find the direct stress due to bending at off way of the beam and also at the built-in end of the beam. Now let us calculate the direct stress due to bending at off way of the beam, that is at the mid span of the beam. Okay, so now we have to substitute Ixx, Iyy and Ixy here. So before substituting that, let us find mx and my with respect to this off span of the beam. Okay. Now let us calculate, for example, the loads which are acting in y direction that has to produce, that is supposed to produce bending moment about x-axis. So mx is equal to mx. Now I am taking moment with respect to this dotted line. That is nothing but the moment at the mid span of the beam. Now this 50 is the load acting in y direction. 50 into x, 50 into 100. 50 into 100, force into perpendicular distance, that produces a compression. So mx is nothing but minus. So minus 5000 Newton millimeter. And my. So we are finding the bending moments at the mid span of the beam. Please try to understand. Okay. So my. So the x loads will produce this is the load acting in x direction. 80 into 100, and this 80 load produces a tension here, elongation. So it is positive. 8,000. It's nothing but 8,000 Newton millimeter. So now mx is available, my is available. We have calculated already Ixx, Iyy and also Ixy also. Substitute in the above expression, you get the final term to be, that is direct stress due to bending expression. Okay, direct stress due to bending expression, this is nothing but at off span of the beam. Okay, or mid span of the beam. Okay, so sigma z is equal to, when I substitute mx, my, Ixx, Iyy, Ixy, I get sigma z is equal to 0.457x, 0.457x minus 0.798y. So this is my expression at the off of the beam or at the mid span of the beam. Now I have to find out the bending stress, that is the direct stress due to bending at point 1 and point 2, point 3 by substituting the corresponding x and y coordinates, so that I will get the direct stress due to bending at these 3 points and at the off way of the beam, since we have considered the bending moments with respect to off of the beam. Okay, so now let us find out the coordinates x and y, then we will just plug in the values in this expression. Okay. So let us keep this expression as it is. Okay, Okay, we take the points. Okay, points. We are having points as well as the x distance millimeter and y distance millimeter from the centroid. Okay, sigma z is Newton per millimeter square. Sigma z is Newton per millimeter square. So let us draw the tabular column like this. Okay, let us draw the tabular column. So we have how many points? So we are having 3 points in this. So point 1, point 2, point 3. So this is my centroid. With respect to this centroid, for example, point 1, how much is the x coordinate? How much is the y coordinate? This is the second quadrant. X is negative, y is positive. X is negative, y is positive. So minus 10.8 is the x value and y value is 19.2. So if you substitute this minus 10.8 and plus 19.2 in this expression, you will get minus 20.257 Newton per mm square, which is the direct stress due to bending, compressive in nature at point 1 at the mid span of the beam. Then at point 2 again here x value is the third quadrant, negative, and y value is minus 4.8. So plug in this value in the sigma z, you will get minus 1.105 Newton per mm square. Similarly, third point, 25.2 x coordinate and y coordinate minus 4.8. Substitute x and y value here, you will get 15.346. So this is the tabular column which shows the direct stress due to bending at the mid span of the beam, halfway of the beam. Okay. So similar type of tabular column we have to prepare now. Okay. With the same x and y coordinate, we are trying to find out the bending stress at the built-in end, at the fixed end. Okay. This expression is not valid for the built-in end because we are going to take moment with respect to the fixed support where this force will come into picture. Again, the arm distance, moment arm distance will vary. So we have to find the bending moments mx and my again. Okay, so now let me erase these values, erase the sigma z values. Okay, whatever be the force, whatever be the magnitude of bending moment direction, this x and coordinate doesn't change because geometry remains as it is. Geometry remains as it is. Okay. Now mx. Now we are trying to find out at the built-in end. At the built-in end. Okay. So mx is equal to 50 into 200 about x-axis. 50 into 200. 50 into 200. That produces a compression. So minus. Then this 50 into 100 that produces a tension about x-axis. So plus 50 into 100. Okay. So now this gives mx is equal to minus 5000 Newton millimeter. Minus 5000 Newton millimeter. Then my, which is the bending moment about y-axis due to the loads acting in the x direction. So here only one load is acting, 80 into 200. So 80 into 200. So that produces a tension. Here. Okay, it is acting like this. That produces a tension. So which gives rise to positive bending moment my, 16,000 Newton millimeter. So now we have arrived the new bending moment values mx and my, and we have got already ixx, iyy, ixy. Plug in all the values in this expression. You will get one new expression for sigma z. So that is coming out to be sigma z, for example, a new expression. When you plug in this new bending moment values, you will get 1.61x plus 0.3125y. So this is expression, bending stress expression with respect to the built-in end. Now substitute this x and y value in this expression. You will get sigma z value. Now when I substitute for the point 1, I get minus 11.388. Here minus 18.88. You can stop with 2 digits also, you wish, and 39.072. So these are the bending stress or the direct stress due to bending at the built-in end due to the external loads acting in x and y directions. So the plus sign says that the nature of the bending stress or the nature of the stress is compressive, and the plus sign says that it is a tensile, and the negative sign says it is compressive.